short video on tutorial 8, which is the continuation of the finite element analysis of the wind turbine tower using the 3D Experience platform. In tutorial 7, I did this problem and only material nonlinearity was considered. Geometric nonlinearity was turned off. And remember that video was based on the paper that you see here and the YouTuber's work down below. Now I'm going to extend that, and I have saved that video, and it's in this playlist down there. You can see. What I'm going to do is I will activate the geometric nonlinearity effect, and the result that we're going to be comparing our calculations with is this red dashed line. Okay, notice that the solid dashed line was load case 2 material nonlinearity only, which was tutorial 7, and this I did not do the load case 1, which is the solid black line, but now I'm doing the load case 2 geometric and material nonlinearity, and of course the software is going to run until it crashes at this point. So obviously some nonlinear stability occurs here, which is not our goal. Okay. All I have to do is to activate the geometric nonlinearity box here, and everything else is the same. These are the same thing that was used in material nonlinearity also. That's pretty much it. We're going to run it and look at the 2D plot that's generated. Okay, we're going to do the nonlinear geometric effect and nonlinear material simultaneously. The only thing that I have to do is to go to the previous model that I created in tutorial 7, which dealt with material nonlinearity only, and activate a switch. And that switch, if you go to the static step here, under advanced, include the geometric nonlinearity, and you say OK. I did not change any of the parameters that I had, time values that I had from the previous one. Everything is the same. The only thing that I did, I included a geometric effect. Okay, and now we're gonna run it. All the legwork has been done. 2D plots have been generated, at least the format for it, and all we have to do is to run this thing, and because it's going to take a while, I'm going to stop the recording, and when it finishes, we're going to come back and look at our graphs. Okay, let's wait for a few iterations here, make sure everything works fine. And it should, because I haven't done anything from the previous run that worked successfully. Of course, I killed that job at, I believe, 83%, but we'll see how it goes with this one, okay? Okay, the iterations are going to start momentarily. I may have to go and reduce the minimum time step, but we'll see how it works. I'm going to stop the recording here. Okay, after 10 minutes, clock minutes, I am at 62%, and this is how the iteration is going. And I can also look at the plot here. Looks like so. And I'm going to stop the recording once again. Okay, we can see that after about 13 minutes, the software, it says analysis failed due to errors, and I suspect that the time step increment has gone below the 0.005 that I specified. You can see that, and we can close this and look at the results up to this point. So close that. You have to go and get your results by going there. It's going to show you everything up until that point. Okay, that's fine. Move this thing away, and I'm going to turn this thing around. All right, so this is the initial, of course, there's no deflection, and then these are probably elastic. Actually, let's find out. Let's plot the von Mises stress. Remember, the yield strength was about 345, I believe. So this is 1919 elastic. This is 139 megapascal, still elastic. 429, so it's beginning to go into the plastic. If I'm not mistaken, it was actually 345. So anyway, this is going into a plastic region, and go further down and down and down. And obviously, it crashed at that point. So this is fine. Let's go ahead and plot the 2D graph. So here, double click on this. Got. First of all, I want to remind you that this is not correct. It is actually load proportionality factor. So I have taken the actual force, reaction force, and divided it by 1.6 meganewton. Okay. So this was actually mentioned as a note in the YouTube description. So this is not force. It's force, non-dimensional force, or force proportionality factor. And look at what it happens. It goes. This is for load case 2 that we're dealing with. It goes for about 300 millimeter. It goes to about 1.2-ish. And if you compare that with uh, the results here, we are dealing with load case 2, geometric and material nonlinearity. So it's this dashed curve which is shifted a little bit, but it goes. You can see that it goes between 1.2 and about 300. This graph should be shifted to the left, and when you look at the scale, it's going to be close to 1.2, and once it gets shifted to the left, it's going to be around maybe 400 or 300 something. So that quite agrees well with this thing. Now, so we have managed to for the load case 2, managed to look at the dashed curve, black curve here, which was material nonlinearity only, and this one is material nonlinearity and geometric nonlinearity, and it agrees with our results. Good. I don't like particularly this graph here because of the way it's drawn. This actually should have been shifted to the left. I mean, it should be on that thing. Good luck.